Hello everyone, welcome to APS Deep Academy and this is your mentor Swati Joshi. In this class, we will study the Fermi level distribution of electrons in metal semiconductor insulator and in semiconductors intrinsic and extrinsic type. Now, as a part of definition, we see here the definitions. The definition first is the Fermi level is any energy level having the probability that is exactly half filled with electron. Levels of lower energy than Fermi level tend to be entirely filled with electron, whereas the energy level higher than the Fermi level tend to be empty. And this we are considering at absolute zero temperature. Now, what absolute zero temperature means? Absolute zero temperature means 0 degree Kelvin. Why so? Because if we increase the temperature little much, then the electrons in the shells get excited and try to jumping into another shell. As in case of metal and semiconductor, we know that in room temperature they have sufficient energy to jump into one valence band to conduction band. So we consider here 0 degree Kelvin or absolute temperature. Now first discuss the definition 1. According to definition 1, first we will discuss the Fermi Dirac distribution function, which is nothing but 1 upon e to the power E1 minus E2 divided by kT. Now this is nothing but a Fermi Dirac distribution. Fermi Dirac. Fermi Dirac here, Fermi is one scientist name, Dirac another scientist name. So Fermi Dirac distribution function defined that how much probability of electron in a shell is there. So to derive this formula, it is beyond the course of this syllabus, which is basic electronics, but in higher studies we study this. In semiconductor physics basically we study this, but till now we will study that this is the basic function, Fermi Dirac distribution function, from which we calculate our Fermi levels in metal insulator and semiconductors. Now let us discuss one case here. If this is our insulator, let's say, okay, insulator. Now we know that this is conduction band and this is valence band and this is the EG. Now we consider that Fermi level reside in between conduction band and valence band. So energy of Fermi level is EF and energy of conduction band is EC. Similarly, energy of valence band is EV. Now we will derive our three functions here. First is energy level higher than the Fermi level tend to be empty. So we are considering the case of conduction band. That why conduction band is empty in case of insulators. Okay, let us discuss. Now we are considering here the energy of EC because we are calculating for conduction band. So 1 upon 1 plus e to the power EC minus EF, because the second level here is not the valence level but the Fermi level. In between we are considering that from Fermi, above the Fermi level, the conduction band which is empty, because in definition it is written that energy level higher than the Fermi level tend to be empty. Okay, now we will divide it by kT. T here at 0 degree Kelvin, so kT will be almost 0. Okay, so 1 upon 1 plus e to the power, whatever the EC here, it will be always positive because it is in the above of the EF. So the energy in conduction band is always higher than the EF. So we consider this as a positive infinity, positive value of anything. And we divide it by 0. So anything we divide by 0 is nothing but infinity. So this is 1 upon 1 plus infinity. Now if I am adding anything to infinity is always an infinity. So this is the function 1 of 1 upon infinity and it is nothing but 0. So the probability here that electrons we will find in conduction band at absolute 0 in insulators or any metals are 0%. Clearly understand this? Now we will study the second case, that levels lower energy than the Fermi level tend to be entirely filled with electrons. See the second case here. Okay, now in second case we will consider the energy of valence band. So PeV we are calculating 1 upon 1 plus e to the power. Now here EV minus EF by kT, because we are considering the energy band EV first and then EF. So whatever the answer of this, it will be always negative in nature, and kT is 0. So we can write 1 upon 1 plus e to the power minus infinity. Clear? Okay, now this minus infinity we can write 1 upon 1 plus 1 upon positive infinity. Clear? And this is 1 upon 1 plus 0. Similarly, 1 upon infinity is nothing but 0. So if this is 0, then we considering this is 1 upon 1, which is nothing but 1. And probability of 1 means nothing but 100%. Clearly? So you clearly understand that probability of having electron in valence band is 100%. So energy band lower than the Fermi level, electron finding probability is 100%. Now we will consider the case of EF, that how EF is half of the electrons, filled with half electrons. Now the case of EF. So probability at EF will be 1 upon 1 plus e to the power, here EF. One upon 1 plus EF. First band is EF, second band is also EF because we are considering it in middle. So if we cancel out EF from EF, it is nothing but e to the power 0, because it divided it is kT, which is already 0. So what is e to the power 0? E to the power is anything which is, so here 1 upon 1 plus 1. Why so? Because anything which is power in 0, it is 1 always. So this is nothing but 1 upon 2, and 1 upon 2 is nothing but 0.5, and 0.5 is considered as 50% probability. Clear? So the three case clear here. First one is for EC, second one is for EV, and third one is for middle, which is EF. So this is the case of Fermi level. We understand that the energy level higher than the Fermi level is always empty. The energy level lower than the Fermi level is always filled with 100% probability of finding electron, and at the Fermi level we have 50% probability of finding electrons. Now according to Fermi level, let us quickly draw the energy band diagram in case of metal, insulator and semiconductor. Let us discuss insulator first. So in insulator, that this is conduction band and this is valence band. So EF or Fermi level is in between conduction band or valence band. It is case of insulator. In semiconductor, conduction band and valence band, and in semiconductor intrinsic type. If it is in intrinsic type, it is EF is in middle. And here we are considering the case of intrinsic semiconductor. For extrinsic, I will discuss little later on. So this is the case of metal where conduction band and valence band overlapping. So energy level is also in between conduction band and valence band. So this is also overlapping with two bonds. It means EF is in between EC and EV. Now this is the case of metals. Now here we can see that a second definition is also there. According to this, the highest energy level that an electron can occupy at absolute zero temperature. That what is the highest energy level an electron can occupy? If there are some electronic distribution of electrons in a particular atom, then what is the higher energy level for this atom so that it can occupy the particular shell? So now we will discuss the case of intrinsic and extrinsic semiconductor so that we can understand the second definition very much. Now here we can see that highest energy level that an electron can occupy. In this case we will study the case of intrinsic semiconductor and the extrinsic semiconductor. Now what can happen in intrinsic semiconductor? We already know that EF behaving like it is in middle, so 50% probability, valence band and conduction band. But what is happening in extrinsic semiconductor? We have two types. One is N type and one is P type. So N type, we know that pentavalent impurity. So is this electron is in majority? P type, holes are in majority. So this is like this. If I talk about the energy band diagram of these two, what will happen? Okay, what will happen? This is the conduction band, this is the valence band. And in N type, electrons are in majority. Electrons are in majority. Fermi level, highest energy level of Fermi level, highest energy that electron can occupy, it will be near to conduction band. So EF will be near to conduction band. And the second one in N type, valence band and conduction band. So holes are in majority. So highest energy level that electron can occupy will be near to valence band. So this is the condition of EF here. Why so? Because according to definition, we can see here highest energy level electron can occupy at absolute zero temperature. What is the highest energy level electron can occupy at absolute zero temperature? So highest energy level in intrinsic, we already studied this case in between 50% probability. In N type, what is happening? Electrons are in majority. We are doping electron into this intrinsic type semiconductor. We are making it extrinsic. So the electrons are little higher than earlier system. If electrons are in higher, so what will happen? The Fermi level will shift toward the conduction band. Why so? It will shift because the electron are in higher probability than the holes here. Second one is our P type. In P type, what is happening? We are reducing the term electrons here and increasing the empty space which is holes. If we are reducing the electrons, so the Fermi level will shift towards the valence band, and this is the condition which we called in P type semiconductor. So as part of your examination, I think this is too much. And as for learning, we know that probability function is only for the distribution of electrons in the shell. So you have to learn that it is nothing but 1 upon 1 plus e to the power e1 minus e2 by kt. And if numerical comes, you can directly put the values on that, because the derivation is not in basic electronics syllabus yet. So this is the enough for Fermi level. I think I already told you so much of that. At absolute zero temperature, you have to take this, and absolute zero temperature is 0 degree Kelvin. And definition 1 and 2, I already explained it in detail. If you have any query regarding this, kindly mention on comment section. I will try to clear this, and numerical based on this we will also do in later on. Okay. Thank you so much.